Good evening everyone. Today I will explain about my research paper for machine learning application with the title is a transfer and deep learning based method for online frequency stability assessment and control. This article already published in IEEE Access in 2021. So fast and accurate prediction and control of our system dynamic frequency after disturbance is essential to enhance power system stability. Machine learning methods have a great potential in harnessing data for online application with accurate prediction. This paper proposes a two-stage novel transfer and deep learning-based method to predict power system dynamic frequency after disturbance and provide optimal event-based load shedding strategy to maintain system frequency. The proposed deep learning models combine CNN and long short-term memory (LSTM) to harness both spatial and temporal measurements in the input data through four-dimensional tensor input construction process including 1, 2, 3, 4 that already present in the slide. In addition, this simulation result is present in IEEE 118 bus system to verify that CNN and LSTM method not only greatly improves the timelines of online frequency control, but also present good accuracy and effectiveness. In addition, the test case in the New England 39 bus system and the South Carolina 500 bus system also validate that the transfer learning process can provide accurate results even with insufficient training data. In this slide, we will discuss about CNN and LSTM that are already proposed for architecturing. So, to extract the rich information from the spatial temporal dynamic measurements across different time intervals, a CNN-LSTM method is proposed with the architecture shown in Figure 1. So, in Figure 1, we can see several parts from power system, time series data for the tensor, CNN layers, LSTM layers, and dynamic frequency. So, the proposed deep learning model consists of CNN and LSTM layers. In the proposed architecture, the fully connected layer in CNN is replaced by the CNF layers to learn the generic features due to the capability of encoding spatial information, which is a key factor for the following LSTM. From the architecture, we can see that the temporal tensors are selected as input and featured in this input are first extracted by CONV layers. Then pooling layers are adopted to reduce the spatial size of the representation learning by CNN. After that, the flattened layers convert data to 1D array as the input to the LSTM layer. Finally, temporal features are extracted by LSTM and go through the fully connected layer to regression analysis. In this section, we will discuss about transfer learning principle. In a practice, the transfer learning process is usually implemented by freezing some neuron layers in the source machine learning model that it's well-trained model and retraining the last one or two layers based on the data obtained from the new system. This frozen layer is usually used to extract features from input. For power system dynamic frequency prediction, the proposed CNN-LSTM model can be trained on one source system and then transferred and tested on new system, where few available sample data can be obtained. The CNV and LSTM layers can be directly applied to the other system, which could greatly help reduce the data sampling and training costs, as shown in Figure 2. In this section, we will discuss the transfer and CNN-LSTM based frequency prediction. So for the first part of this section, we will discuss input feature selection. Adequate and high quality data are the basis for ensuring the accuracy of machine learning models. Before building a CNN-LSTM model, the input data must be filtered and organized based on the characteristic of power system frequency stability. In addition, the proposed CNN-LSTM method can process temporal data. Therefore, state variables at different times will also be captured as input for CNN-LSTM. For the input, furthermore, The data is for the input features adopted in SLSTM is shown in table 1, which consists of a 5 number and input feature. So we can see in the first number for the input feature is active power of each generator PEI from T0 to 3FT, which means 30 represents the moment when a disturbance occurs and FT the sampling period. It means that the critical state variables from the moment when disturbance occurs to the third sampling period are captured. The input features are summarized in table 1 that are already mentioned before. And for the second part of the section, we will discuss about input tensor construction. As stated in section 1, the input for CNN-LSTM are 4D tensor data, which consists of rich spatial temporal information. In order to construct 4D tensor, we first build 3D tensors that include the system network data. In this section, we will discuss about model training and transfer learning. After obtaining the 4D tensor inputs and the corresponding output from a specific test system, we can perform a training process to obtain a well-trained CNN and LSTM model. Then, the trained CNN and LSTM layers will be frozen and only the last fully connected layer will be retrained when applying to prediction text for a new test system. We can see the overall procedure in here using pseudocode for sample generation and the flowchart of the proposed scheme start from dynamic simulation, sample generation, well-trained CNN-LSTM model, and until the well-trained CNN-LSTM model 2, and we can see the optimal load shedding strategy and the end of the process. So this is the how to train model in through machine learning application of deep learning. In this section, we will discuss about the simulation result and sample generation. The proposed CNN-LSTM based power system dynamic frequency prediction and optimal load shedding strategy are tested on IEEE 100 bus system. After that, the trained model is transferred and applied on the New England 39 bus system and South Carolina 500 bus system, or we can call active SG500 to test the performance of transfer learning. Regarding sample generation, in this paper, the dynamic datasets are simulated on PSSC and a generated tripping determinant is set at 0 seconds to cause power loss and dynamic frequency. The simulation time is 40 seconds and the sample rate is 100 Hz. In order to simulate different operation states and generate enough sample, the load level is set to 120 with different scenario for 40%, 45% until 100%. Under different operating modes, generator tripping faults are applied, and system state and dynamic frequency response after disturbance are measured and collected. A total 2040 sets of sample data are collected. There are 990 samples categorized as unstable samples, which require load shedding controls. For these 990 samples, a pre-optimization process is applied to obtain optimal sample output. In this case, 85.3% of samples are used for training, and the remaining 14.7% samples are adapted as test data. In this section, we will discuss about the frequency prediction and performance analysis. In this section, we adopt the CNN-LSTM model to predict the COI frequency after fault, which can provide more information than previous study in the literature on the minimum and maximum frequency prediction. In order to test performance of the CNN-LSTM models among 2040 samples, 1,740 samples are randomly selected as the training set, and the remaining 300 samples are used as the test set. Training and test process are implemented on the Keras framework. In order to evaluate the prediction performance of three methods, the following index is adopted, which including mean absolute percentage error (MAPE) and root mean square error (RMSE) between predicted curves and actual curves, steady state frequency Fs and the minimum frequency Fmin after disturbance. So we can see the error comparison of minimum frequency among three methods. First is CL, NNN, and SFVM. So we can see the frequency deviation for each transfer, for each machine learning application, and we can see also the different tests about the test, how test sample with the frequency deviation for the each part of machine learning. And in the figure 6 we can also see comparison of minimum frequency prediction among three methods. It is so that using A and N, the frequency will be much lower for frequency prediction compared to the other concept. In this section, we will discuss about the load set amount prediction analysis. Based on the prediction results, there are 141 cases in the test sample that need to set load in order to maintain frequency stability. Therefore, the measurement of these 141 cases are inputs to the steady state CNN-LSTM model for optimal loading setting strategy. The predicted optimal load setting amount on load 54 is compared with the actual output value of the sample, as shown in figure 7. The optimal loading setting amount of each load node prediction is very close to the optimization result in the test sample, with the maximum power error is 0.015 VU, which indicates that the model can provide highly accurate prediction test result. The control effect of load shedding on test case 10 is shown in figure 8. From this figure, it can be seen that the proposed load shedding method can ensure that the minimum frequency is maintained above 59.5 Hz after a fault occurs. So this is the optimization with load shedding, and this is without load shedding. The frequency will be much greatly improved with load shedding application. Also, as I already mentioned before, the prediction of load shedding amount, the error on the slightly, or we can see the value of very 0.015 is very close to 0. So I think this is the very accurate prediction to see the load shedding. And this is the last part of the paper, is conclusion. So for the conclusion, this paper proposed a transfer and CNN-LSTM based method to accelerate and improve the accuracy of dynamic frequency and optimal load shedding prediction process. The proposed method exploits system spatial temporal information and mines the local features of the inputs, which highly improve the performance compared with other machine learning methods. In addition, the proposed learning process significantly enhances the generalization ability of the proportion and LCM, and overcomes the shortage of insufficient data and operation condition changes in real power system, which provides remarkable training with sample generation savings. Simulation results on IEEE 100 bus system, New England 39 bus system, and active SG 500 system validate the effectiveness of the proposed CNN-LSTM method. The comparisons show the proposed approach has a superior accuracy because of the ability to exploit spatial temporal information. Moreover, the proposed method is applicable to online frequency stability management and control the prevent frequency collapse. With more and more reliable energy integrated with modern power system, the future work author want to focus on investigating the impact of energy generation on transient stability and extend the method to prediction of other states such as voltage. And we can see also in table 3 and table 4 about the table accuracy of different methods on IEEE 39 bus system and minimum frequency accuracy prediction comparison in table 4. For table 3, we can see using the analysis of RMCE, the transfer CNN-LSTM has have a good performance compared to the other concept, which also which also related with minimum frequency accuracy variation comparison, which so that using the difference of two kinds test system is present.